We're going to finally start doing some inference. And the cool thing is we're going to lay all the groundwork in Chapter 9. And then in Chapter 10 and Chapter 11, we're essentially going to be doing the same thing, just with different contexts. So it's all going to be inference. It's all going to be significance. So we'll be testing hypotheses. This is the culmination of the class. This is where we've been headed the whole time.
This is it.
This is the final destination.
Can I title my notes Final Destination?
Final destination. We're here. We have arrived. No. 9, 10, and 11 are inference. This is where they're supposed to land in the class. This is what we've been building up.
Alright, I'm ready to take extensive notes.
So here we go. We're gonna do these things. Alright, so
We're gonna do these things.
let's intro. So we were doing inference with confidence intervals, right? But it's kind of wishy-washy, right? We expect the mean to be on this particular interval, right? Now we're going to be able to say, hey, given this data that we have, we're going to be able to actually get a probability of how likely it is that a claim could occur, right? So we're going to come up with some hypotheses. And we're going to actually test against the opposite occurring. We're going to find out how likely that would be to occur given some set of data that we have. So that's what we're going to do with a significance test or inference, okay? So we're going to compare some observed data. And we're going to test it against the claim. All right, so essentially, this activity that we're going to do essentially gets us into what's going on with this. And I'm doing this just because in other lessons it mentions this stuff. I prefer the alternative examples. So we're going to do both. Well, when we do the alternative examples, we'll do it's called it's a really cool example. It's about what direction you tilt your head in the case.
Interesting.
Pretty interesting.
What if you do both? I'm so sore.
From that or?
No.
Okay. All right. So this guy says that he makes 80% of his free throws, and we think he's lying. Exaggerating. It's called lying. So we're going to ask him to shoot some free throws virtually. And so let's go ahead and see what happens.
How do you virtually shoot?
When you use an applet. Here we go.
But how does that test your skill?
It doesn't. So we're going to shoot 25 free throws. But see, what it's doing is this guy actually has like a free throw percentage that he actually makes, right? His percentage that he makes. And if we ask him to shoot a bunch, right? And it's unlikely that if it were to even happen by chance, given that he has an actual free throw value. We'll get to the bottom of it.
Okay.
He's gonna shoot 25.
Whoa, that was a terrible.
No, he was really good. It was like horribly nice.
So it looks like he's at about 68%. Right? Let's do it again.
Yeah. I think he would run.
All this is a All this is just a random, it's just randomly generated.
Like he's able to make it perfectly, it just happens to the rest of the
Can you
life.
get one more?
Once in a while.
You want to do one more? Let's do it.
Look at that, it shows in the same spot.
It's not that good.
Wow, that really brought his percentage down.
I think he's doing it on purpose.
Wow, it's really bringing it down.
Hey, they're not that good.
He was at 68, now he's at 64.
Yeah, let's see what his actual probability. His actual shooting probability is, what, about 65%? So, the idea is we can do a simulation, right? So his claim is that he shoots 80%. We did a simulation and found that his percentage was much lower than 80%, right? So because, actually the probability of him, he actually runs at around a 65% probability. So we have evidence that
He's a liar.
he's a liar.
Freaking
All right. I'm gonna go ahead and do the kiss one during this one because it's better.
Okay.
It's much better.
Can I write it down? Or is it
Yes.
virtual as well?
It's not necessarily.
So is there mouth? Shut up.
So a better example is kissing the right way.
It was in the car and I didn't answer it. I was like, let me just turn that down. It's just ringing.
So, according to the San Gabriel Valley Tribune, it says most people are kissing quote unquote the right way.
Whoa.
That is, according to a study, the majority of couples prefer to tilt their heads to the right when kissing. In a study, a researcher observed a random sample of 124 kissing couples and found that 83 out of the 124
And they're gonna be talking about no.
I think that might be exact. They tilt their heads to the right. So we got a B hat. This is couples. This is the proportion
Like that.
who tilt their heads to the right.
I just found you posted. I was like, why? Because I don't know. And he was like, oh, me either.
Oh, good thing
All right. So we'd like to know: is that evidence that people actually do tilt their heads to the right, or did it just happen by chance?
Well, I feel like both tilt their head. Then it works, because you're starting on opposite sides. But if you're kissing somebody who tilts their head to the left and you tilt to the right, that's going to be awkward.
Your noses are gonna bump.
They're going to go like that.
Yeah. All right. So what I did was I wrote a program, or made it so that our calculator will run this scenario. All right. So I made a simulation for it. So the idea is check it out. With this proportion. If there is actually no preference, right? If people have a tendency, if people go either way, left or right, when they tilt their heads when they kiss, then you would expect that the proportion would be 0.5, right? The proportion of people tilting their heads to the right should be 0.5. If I do this, repeat it, right? So, how unlikely is it to have a proportion as high as 0.669? How likely is it to have that proportion if there is actually a 50-50 chance, right? If there, you know what I mean? You know what I'm saying? If there's no preference, then you have a 50-50 chance of tilting right or left, right? So that's the same as like flipping a coin. So what I did was I had the calculator generate randomly 1s and 2s, okay?
Are you sure?
And we can say, I believe a 1 represents tilting to the right, a 2 represents tilting to the left, all right? So I had this thing do 124. So I did this whole thing, and I believe I did it like 20 times, okay? So I did 124 of the, 124 kisses, 20 times, essentially, right? That's quite a bit. And I believe I did it 20 times. Let's see. Yeah, I ran it 20 times. Just to see. And then what I had to do is I had to count up the number of kisses that were right tilts. So I said, hey, if we come up with a 1, count it. And so each one of these digits on the right-hand side are the number of tilts that were to the right. Okay? So after I did that, I went ahead and graphed those results. And so it turned out that the majority of the time, out of 120 kiss tilts, right? The majority of data is focused in here around 58, I don't know, to 60.
Okay, wait, I
right?
figured out why they were nice quality.
And in fact, 0 times did as many as 83 of them come up as a tilt to the right. Sorry. Yeah. So it's pretty unlikely to happen by chance, right? So we did this chance experiment, and we never ever got as many as 83 ones, right? Or right tilts. So it seems that it's fairly unlikely that this 83 happened by chance, which gives us strong evidence that there is actually a preference. So that last sentence I said is a very important sentence, because that's exactly what we're doing. We're going to be given a claim, right? The claim is that there is a preference in the way that people kiss. They prefer to turn their heads. They prefer to turn their heads to the right, tilt their heads to the right. We did an experiment, or we did an observational study, and we looked and saw that 83 out of 124 did indeed tilt their head to the right.
What percentage of them were right-handed though?
There's no way for us to know. But
I bet you they turn to the right because that's the dominant hand and they just go that way. I bet you. There's bias in your data.
it's not my data.
I mean,
Anyhow, we ran a simulation to see how likely it is for that to happen just by chance. Found out that it is extremely unlikely. In fact, we never found a result as high as 83. And so because it was very unlikely to happen, we have strong evidence that there is a preference. And that's exactly the process we're going to go through as we do inference. All right. So we're going to state a hypothesis. Okay? In statistics and in inference, there are actually 2 hypotheses, okay? You have a null hypothesis, which is noted as H naught, or H sub 0, but we'll call it H naught. So when I write that down, I'm going to say H naught is this, or the null hypothesis is this. That is the language that I'm going to use. And HA, or the alternative hypothesis, will denote as this H sub A that you'll see. Okay? So, our null hypothesis is what we're going to test against. Okay? So, and I think the kissing example is so much better. For instance, in the kissing example, our null hypothesis would have been that the proportion is exactly 0.5, right? If there's no preference, then it should be the case that if you observe 124 people kissing, half of them should tilt left and half should tilt right, right? That would mean that there's no preference. Our alternative hypothesis would be that actually the proportion is greater than 0.5. All right, so these are all of the different forms that our alternative hypotheses can have. Our null hypothesis is always going to be a parameter equals some value, okay? And we're going to either show that the parameter is less than that value, greater than that value, or does not equal that value. In other words, it could be greater than or less than, right? And depending on the situation, you'll have to choose one of these values for your alternative hypothesis. All right? So it's going to be one-sided. In other words, like either greater than or less than. If it says greater than or less than. Pretty self-explanatory, this bottom yellow. It's two-sided if it just says, hey, it's just not this, right? That means it could be either less than or it could be greater. Pretty simple stuff. Really not that. All right, so you should, these hypotheses should not be affected by the data. This is not super important. You're gonna never, ever use a statistic. You're always going to use a parameter value for your hypotheses. Okay, so not p hat, but p. Not x bar, but mu. And so on, right? So if you use x bar instead of mu, you will get points taken.
Never use parameter.
Yeah.
I don't remember the difference.
In other words, in the bottom it says it's never correct to write a hypothesis about a sample statistic. Always got to be a parameter.
Wait, so you will
Never use x bar or
never
p
use a
hat.
statistic or never use a parameter?
Never use a statistic
Okay, you told me.
in your hypothesis. Always use a parameter. I pretty much just went over this. Okay? This is exactly what we just did with the KISS test. I think the KISS test one is just so much better. We never ever found a value, right? And essentially, the probability that that would happen was 0, right? So low that we would say it's impossible that it happened by chance. And that's what this is saying. We're talking about the free throw shooter. All right. So, there are two different possibilities or outcomes when we make a hypothesis. Either that the null hypothesis is correct, or the alternative hypothesis is correct. And the way that we say that in statistics is we either accept or reject the null hypothesis. So, if the probability that whatever event occurred that we have, whatever statistic occurred, if the probability of that event occurring is super high, then we will fail to reject the null hypothesis. In other words, it's probably correct, right? If the probability that we get a certain statistic is very low, then we'll fail to reject, so then we will reject the null hypothesis, meaning that the null hypothesis is incorrect. And the way that we're going to do that is we're going to get a p-value. So we're going to perform some statistical calculations and we'll get an actual probability. If our p-value is extremely low, then we will reject the null hypothesis. If our p-value is very large, then we will fail to reject the null hypothesis. And that's what I just said, right? I'm getting way ahead of these slides. In a nutshell. So there's no rule, but we choose an alpha level, okay? There's not a rule, but honestly, 0.05, okay? If you get a probability, in most cases, okay, the one that we usually default to is alpha equals 0.05. So if you have an alpha level of 0.05 or less, then you'll look at your.
It's not even a real pocket.
It's just. So if your alpha level is stated to be 0.05, if you come up with a p-value that is less than 0.05, then you will reject the null hypothesis. If you come up with a p-value greater than 0.05, then you will fail to reject the null hypothesis. Yep. Like 5% chance, essentially, of it occurring.
I look at this in chemistry.
You probably. Alright, you must actually memorize these. You've got to know the difference between a type 1 error and a type 2 error, okay? This is how I remember it, okay? So a type 1 error is you reject the null hypothesis when the null hypothesis is true, okay? A type 2 is when you fail to reject the null hypothesis when the alternative hypothesis is true, okay? Okay, you should have rejected it but you did. That's a type 2 error. Okay? Type 1 error, you reject it, but you shouldn't. Okay? So that's how I remember. You failed to reject. That's how you remember. Okay? It's just logically false or about rejecting the null hypothesis. In type 1 and type 2 errors. We'll get some practice with type 1 and type 2 errors as well. I have an exercise because it's kind of weird when you get it and you get a context. It's kind of weird to figure out what's what, but after a little practice, it's not that deep. So there we go. 9.1 in a nutshell. Tomorrow we'll do some examples, and then we'll get you into doing some of this.